In this video, we will apply the concepts we have covered in the first two lectures on probability into a very important application called Bayes' theorem. So specifically, we'll call upon the multiplication rule, the idea of intersection of events, the conditional probability concept, and then see how, given that we have some prior probabilities on some events occurring, and once we get new information, how we update those prior probabilities. So the statement of Bayes' theorem in a simple two-event case is that the probability, let's say that we are interested in outcome 1, so I'll replace I with 1. Probability of A1 conditional on B is given by, again, the numerator, if you recall the formula for conditional probability, is essentially the intersection of A1B, and the denominator is the intersection of A1B plus A2B. So let me kind of rephrase this. In terms of intersections, the probability of AI conditional on B, according to Bayes' theorem statement, is given as the intersection of AI and B divided by the intersection of A1 B plus A2 intersection B. If we had three prior probabilities, A1, A2, A3, then the denominator would be the intersection of all those three. So here, A1 and A2 are the probabilities that we have before we observe any additional data, so we call them prior probabilities. Probability of B1 conditional on A1 and B conditional on A2 are called, they are the updates that will help us revise our prior probabilities, and they are calculated by getting additional data, doing some more studying, carrying out a survey. So we are essentially trying to update our prior probability weights with new information, and Bayes' theorem helps us see how we can use this new information in updating our probabilities to what we call the posterior revised probabilities. So while before, for example, we had just probability of A1, once we observe additional conditions, probability of A1 and probability of B conditional on A2, then Bayes' theorem is helping us now revise a probability of A1 updating on B. So we say P of A1 conditional on B. It is best to understand this concept using an example. This problem will help us understand Bayes' theorem as well as the idea of prior and posterior probabilities. So let's say a bank issues credit cards and they're interested in whether their customers will default or not. So the prior probabilities are, they have estimated that 5% of the customers will default. So let's say D1 is probability of defaulting. So PD1 is 0.05, and not defaulting is a complement. D2 is 0.095. So these two, D1 and D2, are called prior probabilities, probabilities before any more information. But also they have done some research and they have been able to figure out the behavior of missing a payment and defaulting. So let's say that the bank has found that the probability of missing a payment is 0.2 for customers who do not default. So let M be the event of missing a payment. So somebody who's missed a payment but has not defaulted is 0.2. But a payment could be missed by someone who defaults. In fact, somebody who misses a payment and has defaulted, conditional on default is 1. Because if somebody has defaulted, that means that they have missed the payment. So these two are our updates that we have now got. So our prior probabilities were given by P of D1 and D2. P of M conditional D2, P of M conditional D1 are our updates or new information that we have now got. So based on this, the question says that a customer now has missed one or more monthly payments. What is the probability that they will default? Now notice that initially we just had PD1, probability of defaulting. But now we are being more nuanced. We are saying, what is the probability that they will default given that they have missed a monthly payment? So this is called posterior probability, whereas this is called the prior probability. And Bayes' theorem is giving us a tool to update our prior probability with the new information which we have in this section and to get a more refined version of our probability. So it's given by missing a payment and defaulting divided by all the ways in which somebody could have missed a payment. So PD1 times PM D1 divided by the same term, PD1 times PM given that the default, plus a person who has not defaulted but missed the payment nonetheless. And now we can put in the values here. We know our prior probability of default was 0.05 or 5%. And then probability of missing a payment for somebody who defaults, that is 1. And then we have 0.05 times 1 plus 0.95 times 0.2. And this gives us 0.05 by 0.24 or 0.21. So our probability of somebody defaulting having missed a monthly payment is 0.21. So it is much higher than the general probability of defaulting, which was only 5%. So this is our updated probability, which our posterior probability, and we were able to update our prior of 0.5 using the additional information that we have. Now there is another way of arriving at it using the tree notation that we saw in the first video. So let's say we have probability of default and probability of not defaulting. Probability of defaulting we said is 0.05, and probability of not defaulting is 0.95. Now, suppose a person misses the payment and then does not miss a payment. So probability of missing a payment given that they defaulted, this is 0.2 as the bank has found out. But then the contrary to that would be that they don't miss a payment. Let's say M prime is not missing a payment. I'm sorry, so D1 is default. So this is actually not 0.2, this is 1. And then probability of not missing a payment when the default then is 0. On the other hand, there's more interesting action when somebody has not defaulted. They could miss a payment. So this would be probability of missing a payment given that they have not defaulted, and that probability is 0.2. Or they could have not missed a payment and not defaulted. This will be the complement. This will be 0.8. So now this path is basically the intersection of defaulting and missing a payment This path is the intersection of default and not missing a payment. This path is the intersection of not defaulting and missing a payment. And then this path is the intersection of not defaulting and not missing a payment. So in our case, we are interested in finding out someone who is defaulting, having missed the payment. So we want to find out this arm. But given that they have missed a payment, they could have come on this arm through this first channel, or they could have come to this arm through this channel. So essentially, that's what Bayes' theorem was doing. So Bayes' theorem was giving us probability of D1 intersection M divided by D1 intersection M plus D2 intersection M. And if we look back, this is what we obtained using the Bayes' theorem. So this is the second way of looking at Bayes' theorem, by developing a probability tree. There is a third way in which we can apply the Bayes' theorem. That's called the tabular way. So here, we'll just look at Excel. We again have all our listings here. Let D1 be the event of default, D2 be the event that somebody's not defaulting. Again, our prior probabilities are 5% of default, and then 95% of not defaulting. And we're also told that missing a payment, let B equals M. Missing a payment, if somebody defaults, is 1. Missing a payment for someone who does not default is 0.2. Again, our intersection is given by AI times B conditional AI, so 0.05. And for the second event, our intersection is given by this times a probability, a conditional probability of missing a payment but not defaulting. Which is 0.19. And then we'll look at the marginal, which is the sum of these two. And our outcome of interest is probability of defaulting given that they missed a payment, which is essentially our numerator, which is AI intersection B, divided by our marginal, which is 0.2083 or 0.21. We could have done that for not defaulting but missing a payment, which would be this divided by 0.24 or 0.79. So again, this is the third way in which we can do Bayes' theorem or calculate posterior probabilities given our prior and the update.